Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
I want to talk about consciousness, which is not a topic that if you'd asked me decades ago whether I'd ever be talking about, I would have said that I would, but here I am. What I've sort of realized is that consciousness and features of it, or more to the point, observers like us, are critical in defining what becomes our physics and also, it turns out, our mathematics. So I'll try to explain why it is, I think, that being an observer like us is what causes us to see the physics that we see, not just qualitatively, but in detail in terms of the particular laws of physics that we attribute to the universe. And were we to be built differently, we would have different laws of physics. And I'll try to explain that. So maybe let me start off with a simple case to kind of motivate this. It's a simple case that actually has some mathematical similarities to the real cases we'll be talking about. But let's talk about statistical mechanics. Let's talk about a bunch of gas molecules bouncing around in a box. And the question is, what are the laws of those gas molecules? At a microscopic level, we know it's a bunch of Newton's equations and collisions between molecules and so on. It's a very complicated pattern of collisions and so on. But as far as we humans are concerned, for observers like us, we're operating on a scale large compared to the molecules. And for us, we don't notice all of that detail of all those molecules bouncing around. What we notice instead is just the overall gas laws, the laws of fluid mechanics, the second law of thermodynamics that tells us that even if we start with a sort of simple configuration of molecules in the box, we'll end up with something that looks random after a while, and to which we can reasonably say this kind of looks like a gas or a fluid. So the thing to realize there, as observers like us, for example, on the scale that we're at, we see this kind of simple gas laws, for example. Were we to be operating, for example, on a molecular scale, we wouldn't be seeing that. We'd be asking, what are the details of this molecule colliding with that one? And what's the causal relationships between this collision and that collision and so on? We'd be seeing a different kind of thing. It's the fact that we see the system on, for example, the scale we do that causes us to attribute to it the laws of physics that we attribute to it. Now, there's a little bit more to this. If you say, well, I've got all these molecules in a gas, but what attributes of me as an observer force me to see only the gas laws, only the laws of fluid mechanics, and not more detailed laws? For example, what laws tell me that when I start the gas in a little region in the box in a very simple configuration, and then the gas spreads out all over the box and looks like it's random, what tells me that I can't tell that the thing came from something simple? What tells me that what we're seeing is law of entropy increase, second law of thermodynamics, whatever you call it, that this thing that started simple ended up looking to us kind of random and complicated. And we would say, if we said, what's the entropy of this thing? The entropy is the number of states consistent with what you know about the system. And we'd say this thing has gone to maximal entropy. It's spread out throughout the box. And we wouldn't know, well, actually, it came from this very simple configuration at the beginning. So why is that? Well, the fundamental thing I think that causes that is a phenomenon I call computational irreducibility, which I've been studying since the 1980s. And I should probably explain a little bit about that to you. That's going to be a core phenomenon. It's one of a stack of about 5 ideas that are needed to get to the main things I'm going to talk about. Computational irreducibility. One of the questions about modeling nature is what are the fundamental raw material for making models of the natural world? And kind of the idea since about the 1600s had been, let's use mathematical equations to model the natural world. We'll talk a little bit later about what I think have been sort of 4 epochs in the modeling of nature, of which we have a new one, which has just arrived now. But the kind of the one that we've been sort of living for the exact sciences like physics and so on for the last 300 years has mostly been this idea of let's write down a mathematical equation that describes how the world works. Well, back in the 80s, I kind of got interested in particularly trying to model systems that showed more complexity of behavior, where that kind of mathematical equations approach didn't seem to be the best one. And I got to thinking, what is the fundamental raw material from which we should make models of nature? And I started thinking about, well, what about just using programs? What about using arbitrary sets of rules that one can embody in programs? So then the question is, what do typical simple programs that might be the models that nature uses for different kinds of things, what do they typically do? And that leads us to this kind of exploration of the computational universe of simple programs. That is kind of the core science of my new kind of science in that big book of mine. It's actually something to which we have a new name for it, which is ruliology, the study of the consequences of simple rules. All right, let's look at an example. So here's a quintessential example. This is if it comes to life, well, maybe it won't. Okay, this is a very quintessential example. This is a cellular automaton. You started off from a line of black and white cells. It has a fixed rule here. It follows that rule at every cell, at every step, and makes from that simple rule, as you might have expected, a simple pattern. Change the rule a bit, and you'll get a different pattern. Change it again, you'll get some, again, a rather intricate nested pattern, but still in some sense revealing the simplicity of the rule by kind of the structure of what you get out. But then what you can do is kind of do the sort of simplest computational universe, point a telescope into the computational universe kind of experiment. You could say, what do all possible rules of the kind I've been describing here actually do? And my all-time favorite is number 30, and this is what it does. So there's its rule down at the bottom there. And starting off just from that simple initial condition, it produces this behavior that looks kind of complicated. And if you try and analyze it with math or statistics or cryptography or whatever else, you'll discover that for all practical purposes, for example, the center column of this system behaves like something that seems completely random. A bit like the digits of pi seem completely random once you've generated them. But in any case, the thing that we're seeing is, even from this very simple rule, we just go out into the computational universe and rule number 30 already produces this very complicated behavior. Okay, so the question is, how should we think about this behavior? How do we characterize what's going on here? And so a convenient way to think about it is to think of what's going on as being a computation. We start from some initial state here, then we're computing what's going on. So a question we can ask is, sort of how sophisticated is the computation that's happening in this particular picture? Well, you can go and look at lots of other pictures and lots of other kinds of things in the computational universe, whether you're looking at, you can look at Turing machines, you can look at systems, register machines, you can look at all kinds of things. And the thing that I kind of realized is that once you go beyond a very low threshold of the complexity of the rules, the complexity of the behavior seems to be essentially always equivalent. And so what that led me to was this thing that I call the principle of computational equivalence, which is kind of the idea that once you are outside the domain of essentially easy to describe behavior, you are in the domain of behavior that in a sense is maximally sophisticated in the computation that it corresponds to. So that principle, it's a very general principle. It's a little bit like something like the second law of thermodynamics. It's at some level a provable principle. It's at some level a statement of a sort of law of nature, and at some level it's a definition. It's kind of sort of epistemologically, it's a combination of these kinds of things, much like things like the second law of thermodynamics, to which it happens to be rather related. But in any case, so this principle of computational equivalence, for example, has predictions. Like one of its predictions is that even among these very simplest possible rules that don't seem to have simple behavior, you should see computation universality. So indeed you do. And for example, let's see if I have a good example here. An example of that is, well, here's one. This Rule 110 cellular automaton, which has all these complicated kinds of structures in it, you can, with great effort, show that that is indeed capable of universal computation. And kind of, I guessed this about a very simple Turing machine years ago, and some young chap in England won this prize that we put up by proving that, yes, this Turing machine, which is the simplest one that doesn't produce obviously simple behavior, is indeed universal. Another sort of piece of evidence for this principle of computational equivalence. Okay, So what consequences does the principle of computational equivalence have? The principle of computational equivalence says that as soon as you're out in this computational universe of possible programs, you will tend to find, as soon as you're outside the domain of behavior that's obviously simple, obviously repetitive, nested, whatever else, you will tend to see behavior that is as computationally sophisticated as anything else. So one thing you can then ask is, let's think about comparing sort of the computational sophistication. Let's try to work out, try to think about how would we work out what's going to happen in this Rule 30 cellular automaton. So we can say, well, we're much smarter than it is. We have all of our mathematical methods and all that kind of thing. Surely we must be able to shortcut the actual computational process that's going on in Rule 30. Surely there must be a way to computationally reduce what's happening here. And obviously, there are little pieces of that that can be done. And the thing that we learn from kind of traditional mathematical science is that's been the big sort of badge of honor of traditional mathematical science is you don't have to follow the idealized planet around its orbit a million times. You just plug a number into a formula and you find out what happens without having to trace all those steps. But what seems to be true about things like Rule 30 is that that's not the case, because what we've got here is sort of a competition between the computation that's going on in Rule 30 and the computation that's going on in our mathematics, brains, whatever else. And the claim of the principle of computational equivalence is that those computations are of equivalent sophistication. So in the end, there's going to be no way to kind of outrun this computation. We're kind of forced, the only way we can find out what's going to happen is by doing the sort of irreducible amount of computational work to work out what will happen after, let's say, 1 trillion steps in this particular system. And so, it's very easy to ask questions like, okay, we've got this thing here. We say, is it going to halt? Is it going to, are these structures going to eventually die out? That's hard to tell. We have to sort of an irreducible computational process. We have to keep running it. I think this one after 4,000 steps does eventually sort of give up. But there's no upper bound that we can a priori give on what happens, and we can formulate all kinds of undecidable questions about these systems. And it's sort of interesting that we are immediately confronted with undecidability, and that's going to be relevant when I talk later about mathematics and mathematical observers, that in sort of the computational universe of possible programs, undecidability is a rampant phenomenon. Okay, so we talked a little bit about computational irreducibility and the idea that you can't kind of jump ahead of these systems and see what they're going to do. So let's see, how does that relate to the second law of thermodynamics? Well, one feature of the second law of thermodynamics is this idea that in principle, you can always invert the behavior because the laws of mechanics are effectively time reversal invariant. There's a unique initial and final state, and you can go backwards and forwards. So the question is, even if at the microscopic level you can go backwards and forwards, what does that mean for the macroscopic structure of the system? So this is a particular reversible cellular automaton. Rule 30 doesn't happen to be reversible. This one is. And it has the feature, you start it from this very simple initial state, you run it forwards in time, it makes this complicated pattern, you run it backwards in time, it also makes a complicated pattern. So now you ask the question, well, let's imagine that this is this sort of an idealized model of what might happen in molecules in a gas. And you say, I'm stuck looking at this state here. What can I conclude about what happened before? And the sort of the basic point is, because of computational irreducibility, the only way you can conclude things about what happened before is by doing a certain amount of computation. And when you're dealing with the number of molecules in a gas and so on, that amount of computation is pretty large. And so the basic point is, if you are an observer who is computationally bounded, you are forced to only see certain simple things about what happens in the system. And for example, you can't tell that it really came from that simple initial condition. So in another way to think about this, in statistical mechanics, it's common to talk about coarse graining. It's common to say, we're only going to look at the gas on a coarse-grained basis, and that's how we will make conclusions about it. But the sort of the footnote is, what counts as a valid coarse graining? And that's always been rather obscure. And I think the answer is that coarse graining is being done by an observer like us, an observer who, among other things, is computationally bounded. That the computation that can be done to set up the coarse graining, to either set up the initial condition or, for example, set up how you're doing the analysis, is only something that has a limited amount of computation associated with it. And so it's a consequence of computational irreducibility then that you end up getting systems which will kind of escape the sort of computational boundedness of the preparation of their initial states, or the computational boundedness of the analysis that can be done on them, and necessarily end up with a situation in which you say, oh, I can't tell what's happening. It must be following a law of entropy increase. It must be going to something which I consider to be a random state. So the takeaway from this is the deduction that the second law of thermodynamics is true, the deduction that we can look at fluid mechanics, we don't have to look at the individual molecules, that deduction is a consequence of the way that we are looking at this system. The fact that we are a computationally bounded observer who happens to be, it's sort of a sideshow. It's easier to understand, but it's kind of a sideshow to the main story. We also happen to be big compared to the molecules, but it's enough to say that we're computationally bounded. So the computational boundedness leads us to those particular laws of physics. If we were differently built, if we were not, for example, computationally bounded, we would not conclude that those were the laws of physics. And so this is sort of a first example of where this works. Now, just to give a sort of corollary to this, to understand a few things, people often talk about the heat death of the universe. What happens when the universe it's gone for a really long time and all that's left is this hot gas that has a bunch of molecules bouncing around. There's nothing else left in the universe. What a bad final state for the universe. Well, it's a bad final state for observers like us, because at our way of analyzing what's going on, we just see a bunch of maximum entropy state. But for a different kind of observer who is observing all these causal relationships between collisions between molecules, it can be the most exciting state you can imagine. And so it's, again, something where it matters what the observer is like, what kind of conclusion you make about the system. All right, so that was a prelude about statistical mechanics. Let's talk about the real story. The real story has to do with fundamental physics and our perceptions of space and time, and the fact that I think that the nature of us being observers like us with attributes that I think are sort of core attributes of what you might think of as consciousness, those attributes turn out to be what lead us not just approximately, but precisely to the laws of physics that we know, specifically general relativity and quantum mechanics. And we're going to talk, as I say, beyond that, we'll talk about how that setup also applies to mathematics, and how the very possibility of doing high-level mathematics will turn out to be that the story of why we're able to do high-level mathematics is the same as the story of why we perceive there to be space in the universe. So, okay, that's the prelude. Now let's get into talking about more details here. So the big picture has to do with our physics project, which frankly has been quite amazing to me. Not something I expected, not something I thought would work the way it's worked. I had long been interested in whether there was sort of computational underpinnings for physics, and whether, for example, we could just define some perhaps simple rule that would give us all of the physics that we see in the universe. And I had figured out in the 1990s some aspects of how to do that and how to think about things sort of below space and time and so on. But about 2.5 years ago, 2 years ago, I forget, something like that, with a couple of young collaborators, we managed to make just amazing progress with this. And I think what has become rather clear is that this is kind of the machine code of how physics works. And what's been really interesting about it is that there are many approaches to mathematical physics, whether they're spin networks or causal set theory or other kinds of or categorical quantum mechanics, all these kinds of things, which are essentially mathematical physics approaches that have been pursued to sort of understand things about fundamental physics. They turn out to plug in very beautiful ways to the sort of underlying machine code that we have. And this machine code has as its kind of various approximations, limits, manifestations, and so on, all these various other kinds of approaches to mathematical physics. It's really very, very nice. It also plugs into a bunch of things in theory of computation and mathematical logic and so on. We'll maybe talk about some of those. All right, I'm going to have to go fairly quickly if I'm going to reach the end here. So let me try and outline sort of the basic setup of this theory of physics. First question is sort of, what is the universe made of? And sort of the most basic thing that's in the universe is space. And the question is, what is space? Well, usually you just say space is a place where you put things. That's kind of been where, from Euclid on, that's kind of the notion of space. A point is that which has no part, these kinds of things. The kind of starting point for this model of physics is that actually space is made of stuff. So just like a fluid, for example, is ultimately made of discrete molecules, so we think space is ultimately made of what we can call atoms of space. And those atoms of space are just discrete elements. They're abstract elements. They have no attribute other than that they have an identity, and different elements are distinct. We've started recently using the name EAMS, EME, for this and the sort of the way that this ends up being occurring in other places. But these underlying sort of simplest elements of reality, so to speak, the sort of fundamental atoms of existence, so to speak, which in the case of physics are manifest as atoms of space. Okay, so we have all these atoms of space. Maybe in the universe today, we have about 10 to the 400 of these things. So all we know about these atoms of space is how they're related to each other. They exist in these relations. We can represent those relations as a hypergraph. Simpler case, we could just say a graph where we relate pairs of atoms of space, but in more generality, we're interested in a hypergraph where we relate tuples of atoms of space. And we just say, we've got all these atoms of space, and they exist in this hypergraph. And the first thing to realize is that in the limit, just like in a fluid, you can have all these molecules bouncing around underneath, but on a large scale, you see some kind of continuum behavior. So similarly, that can happen with these atoms of space. This hypergraph on a large scale can behave like the space that we're familiar with. And so and for example, we're not intrinsically saying that there's any coordinate system in which these atoms of space are placed. The only thing we know is they're in this hypergraph, they have relations to other atoms of space. So everything else is emergent. So for example, the dimension of space is something where you can, for example, start at a point in the hypergraph and just look at a growing geodesic ball around that point and say, how many atoms of space do you reach at graph distance r? If the answer is about r to the d, then this is behaving like d-dimensional space. D does not have to be an integer. That leads to a lot of mathematical complexity and a lot of kind of attempts to generalize calculus beyond having integer numbers of variables and things like this that you need. But and it also implies a bunch of potentially observable things like dimension fluctuations in the early universe. We suspect that the universe actually started infinite dimensional and gradually kind of cooled down to be roughly three-dimensional at the present time. But in any case, the main thing is that you can think about sort of the structure of space as consisting of all of these atoms of space. And everything that we know in the universe is just a feature of space. So there's nothing in the universe other than space. So things like electrons and photons and all these kinds of things, these all have to be features of space. In particular, they we think are sort of topological obstructions in the structure of space. They're things like a vortex in a fluid. They're things that are similarly kind of persistent in this underlying network that represents the structure of space. And by the way, the things that we know and care about, like electrons and photons and so on, they are a tiny fraction of all the activity of the structure of space. Most of the activity of the universe is concerned with knitting together the structure of space, not with any of the things that we perceive. Maybe 10 to the 1 part in 10 to the 120 or something might be stuff we care about. Okay, so I've said something about what, sort of what space is in our model. What about time? Well, one fundamental thing about our models is that space and time are very different kinds of things. For the last 100 and something years, people have had this idea that it's very elegant to think of space and time as, just part of some, x squared minus t squared setup and so on. But in fact, in our models, space and time start as completely different kinds of things. Space starts as the extension of the spatial hypergraph. Time is the updating of that hypergraph. So there are computational rules, a little bit like the rules of a cellular automaton, except not in detail, where you're just saying if you see a piece of hypergraph that, for example, looks like this, replace it by a piece of hypergraph that looks like this. And you just keep applying those rules over and over again. And the result of that is that you will build up some structure here. Let me show you an example. Sorry, here we go. Okay. Yeah, this is an example of hope. Wake up. Oh, there we go. That's an example of just starting from one sort of simple initial graph and then applying, in that case, it's just this rule here. You just keep on applying that rule, you eventually get a structure like this. This happens to be, I think, a 2.6 dimensional limiting sort of space that's not quite like a manifold because it doesn't really have, there's no sort of Euclidean space down at the bottom because it's 2.6 dimensional, among other things. But you get all kinds of different structures from this, and that sometimes you can have, I mean, there's some, for example, this one here knits something which is very obviously like a two-dimensional structure. You can also knit things that are rather obviously like curved two-dimensional spaces. And by the way, you can then work out, once you have this hypergraph, you can do things like try and work out what is the not only the effective dimension of the space, but also the effective curvature. You just look at that geodesic ball, and the first correction to the growth being like r to the d is a term proportional to the Ricci scalar curvature, which gives you information about curvature, and you can go compute those kinds of things. Well, okay. So let's come back to kind of the big picture of what's going on. So we have this idea of time is this kind of inexorable, computationally irreducible process of updating this network. Space is the extension of this network. So that suggests that space and time are very different kinds of things. And so how come relativity works and all those kinds of things? Well, you know, I'm realizing I'm not going to be able to get into all these details. Let me just say that the key thing is that for the question is, when you are an observer embedded within the system, what is it that you can be sensitive to? And the most important observation is that the only thing you're ultimately sensitive to is causal relationships between updating events. You don't know sort of how things are arranged because you can't know that until you've been updated. So a sort of simple thought experiment. Imagine the universe was just a big Turing machine, a Turing machine where it just has one head and it's running around the universe and it's updating different parts of the universe. You'd say that couldn't possibly be right because, you know, after all, I can see that you're being updated at the same time that I'm being updated. But how would you know that? You don't know, I don't know you've been updated until I myself have been updated. And if you kind of untangle that, you realize the only thing that you can ever actually be sensitive to is the causal graph that represents the relationships between updating events in the universe. And so, for example, we can, here's a typical causal graph. For one of these systems, those orange pieces are events. Those are updating events. Those are pieces of the spatial hypergraph that got updated. And this is saying which piece of the spatial which updating event had a causal relationship to which other updating events. So this defines a partial order of updating events that tells one what essentially in sort of physics terms, the time-like connections between updating events. These edges are telling one what thing has to follow what thing with respect to effectively to time. So one of the things that then happens is so this is a sort of typical causal graph. And one of the things that the way relativity arises is through a phenomenon we call causal invariance. So basic question is, when you do all those updates in that network, we're just saying, whenever you see a lump of network that looks like this, make that update in that lump of network. But we're not saying when to do which part of the network. So we're just saying, do all those updates whenever you feel like it. Now, it could be the case that different microscopic orderings of updatings would lead to completely different behavior. But there is this phenomenon of causal invariance that is related to confluence, studied in mathematical logic. It's a little bit of a generalization of that, that has the implication that whatever the order of updates, the causal graph that represents the relationship between those updates will always be the same. Here's a simple example. This is, okay, let's see. This is a system where this is not a hypergraph. It's a much simpler thing. It's just a string of A's and B's. And the rule just says that BA is going to be turned into AB. So every yellow thing here is an event. So we can say that's the causal graph of the relationship between events. Which event has to have already happened to provide the input for the next event? So we can make the microscopic order of updating, the microscopic updatings can be different in different sequence, but nevertheless, the causal graph that represents the relationship between these is always the same. And the causal graph is all that we as observers of the universe embedded within the universe are capable of sensing. And so it's the invariance of that causal graph that leads to relativistic invariance. And essentially what's happening is that we can have different foliations of that causal graph. They all lead to they all have the same underlying causal graph. So, and we can even see, even in this system here, even in the system of A's and B's, that's, let me just mention something that, so this is kind of using one's computation to update the system as quickly as possible. This is sort of maximally efficiently updating these events. If we change the foliation that we use, if we change sort of what we consider to be the simultaneity surfaces in time, we will get a different sequence of updatings. And here we're essentially using part of our, we can think of this as using part of our computational effort to essentially move across the system and part of our computational effort to update it. And what you see is it takes longer when we're using part of our effort to move in the system, we have less computational resources to spend in doing the updating. And this is what leads to time dilation and relativity. And it's kind of nice because you can see it very explicitly, even in these string updating systems. Okay, so the bigger picture here is, so you have this notion of time, you have this notion of causal relationships, and then you can ask the question, well, what is the effective theory when you have one of these, you have all this computational irreducibility underneath and all these things bouncing around, what is the effective theory that you get out for what the aggregate properties of space are? Or space-time. And it's kind of like the question of when you have microscopic molecular dynamics, what macroscopic laws do you get out for fluid mechanics? What Navier-Stokes equations do you get out? Okay, so you can do the corresponding computation here, and you can ask, assuming there's computational irreducibility, assuming, for example, that the system remains a bounded dimension, effective dimension, what is the continuum limit of what's happening here? Now, I have to say, there's one of these things where it's another 50 years of mathematics to nail down all of the details of all the limits and so on. I mean, I have a certain degree of pessimism because the second law of thermodynamics is at 150 years and it still hasn't had all of its details nailed down. And this is considerably more complicated. But ignoring those details at a physicist level of taking towers of limits and so on, we can say that sort of the same level of sort of rigor that we can say that we can derive the Navier-Stokes equations from molecular dynamics. We can say that from the dynamics of these systems, we can derive Einstein's equations. So what the effective equations for the structure of space-time here turn out to be exactly Einstein's equations. And so let's talk about how we think about that a little bit. And then let's talk about why that's true, because the why that's true is going to be where the whole observer's consciousness story comes in. So so let's just talk about what it means, some features of this. So for example, we can think about JD6 in this graph. We can think about just shortest paths in space. A little bit more elaborately, we have to think about the way that in simple case, we can just think about a straight line in a shortest path is just a geodesic in this graph. So a question is then, what causes deflection of those geodesics? What causes geodesics to be not straight lines, so to speak? Well, one of the features of this system is we can say, well, there are all these updates happening. And all these updates are essentially events in the causal graph. Every update is an event in the causal graph. And we can ask, how much activity is there in the network? How many update events happen per sort of unit volume, whatever that means, because we haven't defined volume yet in this network. And we can more rigorously, we can say, if we look at sort of space-like hypersurfaces drawn through this causal graph, we can ask, what is the flux of causal edges through space-like hypersurfaces? Okay, which is essentially a measure of the density of activity in the network. Well, it turns out that, to my great surprise, it looks as if one can simply just straightforwardly identify that with energy. That energy is essentially the flux of causal edges through space-like hypersurfaces, or the density of update events in this underlying sort of rewriting system. Okay, so what that means is when we have these geodesics, what we're saying is the density of updating events is what determines the structure of the network, which causes deflection in these geodesics. So essentially the presence, this is a sort of qualitative argument for why the presence of energy in the system leads to the deflection of geodesics, which is the story of gravity. And so you can be much more rigorous about it and show that, yes, it does really follow what you expect from Einstein's equations and standard theories of gravity. Okay, why does this work? What's actually going on? Well, one of the issues here, it's a little bit like in the case of the fluid. The question is, what kind of an observer is looking at all of this? What's being looked at the level where we're saying we can think about space and time, and we can think about this notion of continuum space and so on? That's an observer who has certain attributes. Now, the main attributes that the observer has to have, they're really two. One is that the observer is computationally bounded. The other is that the observer believes the observer is persistent. So, or put another way, that the observer sequentializes time and believes that they experience a single thread of that they have a single thread of experience through time. So it's not obvious that would be the case. I mean, an observer in our models has to be made out of these topological obstructions and this and that and the other. The observer has to be constructed, so to speak. But if the observer believes that the observer is witnessing a sort of single thread of time, that is what is needed to be able to derive Einstein's equations and so on. That's what's needed to be able to set up this whole structure, is that the observer has this belief that they go through a single thread of time. Now, what does that really come down to? What that really comes down to is the belief that the observer is persistent. It could be the case that at every moment, it is the case that at every moment, the atoms of space from which we're all made are changing. Every 10 to the minus 100 seconds, every atom of space is probably turning over into a new atom of space. But how come, but nevertheless, we feel that we are the same us that we were, a second ago. And it is that sort of belief in persistence that is what you need in order to derive things like Einstein's equations from this underlying theory. So in a sense that, and by the way, when we start talking about persistence in time, that's the belief of persistence in time. We can also start talking about like motion, for example. Why is motion even possible in a theory like this? As we move, we're made of different atoms of space. How come pure motion, that is just taking an object and moving it around and it's still the same object, how come that works? Well, it's the same story. It's because we as observers like us conclude that motion works. Observers not like us, looking down at the level of atoms of space, would not conclude that motion works. Think about a fluid. If you are operating at the level of vortices in the fluid, you will conclude that a vortex can move around happily in the fluid. If you're a creature looking down at the level of the individual molecules in the fluid, you have no notion that there is this thing that's being transported around without change. So the fact that there is a concept of pure motion is another feature of something. It's something that's part of what we get from being observers like us, observing these systems in the way that we observe them. And so I think that these are sort of core aspects of how kind of our consciousness affects the laws of physics that we perceive. That is, that this computational boundedness and this belief of persistence, which leads to this idea of a single thread of experience in time, that's what leads to the Einstein equations. And it's interesting that such a sort of a generalized statement about being an observer like us can lead to something as precise as the Einstein equations. It's very similar to the fact that they can lead to the second law of thermodynamics, or pieces of this lead to second law of thermodynamics and fluid dynamics and so on. But it's, I think, interesting that that's sort of a consequence of seeing things that way. All right, so that's and if we were that's sort of the logical chain is an observer, computationally bounded, believes in persistence, will conclude that the universe follows Einstein's equations. By the way, it's not obvious that the universe will follow any laws at all, because down at the level of atoms of space, there's all this computational irreducibility. There's all sorts of complexity. We can't figure out anything. We wouldn't be able to predict anything about what's happening. It is a very non-trivial fact that we have found a slice of computational reducibility in which to live, so to speak. And we can attribute it to, you can make all kinds of arguments about sort of why it's inevitable that we have to live in a slice of computational reducibility. But the fact is, because we're observers like us who have found this particular slice of computational reducibility, that slice of computational reducibility is what gives us the laws of physics as we know them. Okay, so that was about general relativity. Let me talk about quantum mechanics a bit, and then I want to talk about the implications of this for metamathematics and other kinds of things. Okay, let's talk about quantum mechanics. So one feature of these models is that I said you do these updates whenever and wherever you feel like. That means that there are many different possible histories for the universe. Each possible sequence of updating events will lead to, in a sense, a different possible history for the universe. And we can see that at a very straightforward level this is just a string rewriting system. Let's see. Here we see many different threads of history. Each one of these things is rewriting the string in a different place and leading to different results. And this particular system is confluent in the sense that every time there's a branch, there's also a merge. That's what leads to, among other things, causal invariance. But in any case, the point is that there are many different threads of history here. Okay, so the key thing about quantum mechanics, the key thing in physics about quantum mechanics is it is a story of there being many threads of history. You know, in classical physics, you throw a ball, it goes in a definite trajectory. There's one history for what happens in physics. In quantum mechanics, the idea is that there are many threads of history, and we get to perceive merely certain combinations of those threads of history. Okay, so the story turns out to be very similar to what happens with general relativity, that we as observers of this system are sampling. So every one of these things we can think of as a different quantum state. And we can think about these, so for example, let's say we are dealing with this combination of states. That will be a superposition of multiple quantum states. And we can ask ourselves, so then we can ask, well, how do we actually observe this? What do we think corresponds to a constant moment in time? What actual states do we say are actually together at the same moment in time? Well, in any case, the thing we can do, one thing we can do here is to, let's just think about a flat foliation like this. One thing we can do is we can try and map out what is the kind of relationship, what are the entanglements between these states. By entanglement, I mean something which is the same as quantum entanglement, but here we see it explicitly in terms of common ancestry in this, what we call multi-way graph. So from this, you can make this so-called branchial graph, which is essentially a map of the entanglements between states. And so this thing is kind of laid out in a form of space that isn't physical space. It's what we call branchial space. It's a space of possible quantum states. It's a map of entanglements and so on. And this branchial space is something that corresponds in quantum mechanics. It seems that distance in branchial space is essentially quantum phase. And that it is a non-trivial piece of mathematics, what the coordinatization of branchial space should be. And we haven't figured that out. We have a bunch of examples. But the qualitative picture is that position in branchial space essentially corresponds to quantum phase. So let's talk a little bit about what that means. One thing that means is the question of evolution, time evolution in quantum mechanics, is a story of what happens to these paths that are going through this multi-way graph and so on. And what turns out to happen is it turns out to be exactly the same story as in space-time, that what's happening is there's a question of what happens to the GD6 going through this essentially multi-way graph. And what happens is when there is activity in this graph, which then these GD6 are deflected. So in other words, just like gravity in space-time is a story of when there is activity in the network, then there will be deflection of GD6. Similarly, in this branchial space, it's the same story. When there is activity in branch time, in this kind of generalization of, in this alternative space-time that is branchial space, when there is activity there will be a deflection of GD6. Now, since I mentioned that sort of the coordination of this corresponds to quantum phase, what that's saying is when there's activity, which we identify as being energy, more accurately Lagrangian density in the system, that will deflect GD6. So it will change the quantum phase. Well, so we know the Feynman path integral is precisely a story of how the aggregate effect of Lagrangian density changes quantum phase. So the conclusion of this is that, rather surprisingly, general relativity and the path integral are the same theory. They just played out in different kinds of space. General relativity is played out in physical space. The path integral is played out in branchial space. And we can say this in both of these situations. We can say much more precise things. For example, there's a precise correspondence between what we have in these multi-way graphs and so on, and categorical quantum mechanics. The correspondence with quantum field theory is more complicated because that involves spatial degrees of freedom, and you have to deal with space, time, and branchial space. And that's just a complicated thing that we're still, and many people who are working on this are still deeply embroiled in. But the basic idea here is that there's this notion of branchial space, and branchial space is the space of quantum states, and quantum mechanics is the story of motion in branchial space. That's and the analog of gravity is the change of quantum phase in which is motion in branchial space. Okay, so how does the observer come into this? Well, the observer, just like in physical space, we have a certain extent. We are not looking at individual atoms of space. We're looking at large clumps of atoms of space. And that's why we conclude that there is something like continuum space. So similarly, we are extended observers in branchial space. But this is a little bit more kind of brain twisting to understand what's going on. And I'm not sure we've finished the understanding of this. But here's the basic point. In the multi-way graph, the universe keeps on branching. It also merges, but it keeps on branching and merging and so on. But we are embedded in that. And so we are also branching and merging. So in a sense, quantum mechanics becomes the story of how does a branching brain perceive a branching universe? How does something which is how do we, with our consciousness, so to speak, continually branching, perceive the universe, which is also continually branching? Okay, so it turns out that the key idea is, okay, we're continually branching, but we don't think we're continually branching. Just like we mentioned, we have this belief that we are persistent in time with respect to space-time, and that we can move around in space and be the same thing as we move around. So similarly, when it comes to this branching process, we believe that we are persistent and that there's just one history of the universe. And so one question is, so that means that even though the universe is branching and we're branching as well, we are conflating all those branches that happen inside us. We're conflating together because we believe that there's one history for the universe. And so the question is that consistent? We could do that, and then we could find out, oh my gosh, we assumed that everything was conflated, and a little bit further down the line, everything's inconsistent. Well, causal invariance is what tells one that that can't happen, that in the end, everything must be consistent. You make some assumptions, and right now, well, things look a little bit inconsistent, but later on, they will all have to become consistent. And that's kind of why we think that there's an objective reality to things, even though we're branching all the time. Now, it's worth saying that in all of these setups, there is, with great effort, you can see around kind of our usual sort of coarse-grained perception of what's happening. So, for example, if you think about fluid mechanics, if you are looking at Brownian motion, or you're looking at hypersonic flow, you will see down to the molecules. It matters what the molecules are like when you are traveling at Mach 20 or something. Similarly, we are very much looking, in the case of general relativity, for places where you can essentially make a space-time microscope and where you can see below the structure, below this continuum structure that we perceive as observers like us. We suspect that there are examples of that, for example, in supercritical black holes and other places, and some black hole merger kinds of places where you may be able to do that. Now, in the case of quantum mechanics, we have been able to see, in a sense, down below the level of the continuum. We're able to see actual quantum effects with H-bar and so on. That's something that was a consequence of the invention of amplification about 130 years ago or something, that we're able to start seeing those kinds of effects. Now, our particular model has all kinds of predictions about there being a maximum entanglement speed that is a maximum speed, just like the speed of light is the maximum speed in physical space. There's a maximum entanglement speed, which is the maximum speed in branchial space, and that may be observable in either cosmology or in various kinds of condensed matter physics experiments and things like that. But the main point here is, as far as why we perceive the things we perceive, the claim is, the reason is because we're observers like us. And the observers like us with these two attributes are believing that we are consistent and persistent and having this computational boundedness. And those two attributes, again, seem to be what lead us to quantum mechanics. So we're saying that these attributes lead us both to general relativity and to quantum mechanics, and by the way, also to statistical mechanics. So the three sort of big theories of 20th century physics, they're all consequences of the fact that we are observers like us. Okay, so that's a little bit on physics. Let's turn to, I should explain the fact that there is a coherent thing to say about what happens, even in these systems that are full of computational irreducibility, is a non-trivial fact. And it's a fact that I think has implications beyond just physics. So for example, one of the things that, let's see if I can pull this up. One of the things that I've been excited about recently is this idea of kind of this notion of multi-computation as being sort of a general paradigm for thinking about science. And this is going to relate to consciousness very much in a moment here. So the issue is, if you're going to make models of things, what are those models like? And I think there have been sort of four epochs in the creation of models for things, and they can be kind of classified in terms of their treatment of time. So, you know, in antiquity, we were dealing with kind of structural models. Just the world is made of things like this. It's made of atoms. It's got epicycles there. It's made of something like this. And there isn't a specific immediate reference to time. Then we get to the 1600s and mathematical equations. The mathematical equations contain time as a variable. It's, you know, you can turn the knob and change time to wherever you want by changing the value of that variable. Then 1980s, things like lots of adventures of mine, trying to introduce this idea that programs are a way to model things in nature. And by the way, it's despite all the naysaying, I think it's fair to say that in 20 years later or something, that the majority of new models that are made of anything are now program-based models. So after 300 years of it being equation-based models, we've seen a transition in just a few decades to program-based models being sort of the dominant models that get made for things. But one feature of those program-based models is not like mathematical models where time is just a variable. Instead, here you have a program and you just say, go run the program. And when you run the program, you're going through a series of steps. And time is that computationally irreducible process. It's the computational irreducible thing that you get by running the program. So there is a definite notion of time here that is associated with computational irreducibility. Okay, so now we get to this multi-computation story, these multi-way systems where you have many possible rewrites that can happen at every step. And here, there isn't a single notion of time. Time is multi-threaded, and it's not, you can't necessarily say what happened in the system at time X. And the only way that you can perceive anything about the system is to be an observer who conflates certain threads of time. You have to have an observer in the system to conclude anything about what happens with it. Well, this idea of multi-computation and making models that are based on multi-computation seems like it's a pretty good way of approaching a lot of different fields. And I'm not going to talk about all of these. I'm happy to answer questions about them. We're steadily going to try and work on these different areas. But let's talk about molecular biology, for example, or chemistry. So imagine you're looking at a chemical process. You have a bunch of molecules, they're bouncing around, they are having chemical reactions with each other and so on. One thing you can always do is to zoom out and say, I just want to know the concentration of every chemical. You'll get this reaction network, which is in fact a multi-way system. And if you want to do chemical synthesis, you'll say, find me a path that gets me to this particular drug output in the best possible way, going through this multi-way graph of chemical reactions. But there's a lower level of that, which is looking at the individual molecules and their interactions. And at the level of individual molecules, we're seeing, we see all these causal graphs and all kinds of other things. A molecule interacts with another one, which then comes back to interact with the first molecule and so on. There's lots of detail about how these molecules interact. As far as chemistry is concerned today, we don't care about any of those details. Doesn't matter what the history of that molecule was. All that matters is what the concentration of this chemical was and so on. The question is that in fact all that matters to molecular biology? So for example, if you look at the history of molecular biology, people didn't know before 1953, people didn't know that individual molecules could contain huge amounts of information. They just thought there are different kinds of molecules and they interact and so on. Then it turned out DNA can store huge amounts of information. Well, I think the same thing is going to happen again. I think that it's going to be the case that it turns out that all of those causal relationships between molecular interactions actually do matter, even though they're kind of equivalenced out when you do chemistry. Those things matter. And so then the question is, for the point of view of molecular biology, what is the appropriate chemical observer? Is the chemical observer something which just says, oh, all we care about is how many of this kind of molecule there were? Or is the chemical observer something that looks at more details? Well, I don't know how this is going to work, but it's very clear that on membranes, for example, you have at a very microscopic level, you have a lot more interest in the details of individual molecules interacting and then another molecule and so on than at the level of chemistry. So I think it may be the case that we can make kind of a different theory of molecular biology that's based on looking at things in this kind of multi-computational way, starting from all these things like causal graphs and so on, and then building up to something which is kind of like general relativity. So one of the things that's the case is as soon as you have one of these multi-computational systems and you have an observer like us, which by the way, the molecular biology observer might not be, but if you have an observer like us, then you inevitably have something like general relativity. And in fact, not just something like, you have precisely a theory that is general relativity. By the way, since we're still in the middle of a pandemic, immunology is another area to which this is highly relevant. The basic story is there's a shape space of antigens and antibodies, and it seems very likely that there's kind of this network of you have an antigen comes in, antibody, you are randomly generating one of 10 billion kinds of antibodies. The antibodies that are sort of close to the antigen in shape space will bind to it. You'll amplify those antibodies. To the antibodies, there will be anti-antibodies, and you'll build up this kind of dynamic network of antibodies and so on. And I think it's likely that that dynamic network, and there have been various theories about this over the years, is what stores a lot of immunological memory. And so the story of the details of causal graphs and things becomes the story of where immunological memory is. And again, it becomes a question of what is the immunological observer, so to speak? What is the thing about all this microscopic detail that actually matters to us? What is the way that we observe that? Okay, I said I would talk a bit about mathematics. Let me talk about that. And first thing I want to say is, that the structure of mathematics is, it's fairly easy to see that the kinds of things I've been talking about are kind of related to sort of things in mathematics. Let's see, when in doubt, go find it here. Let's see, okay, there we go. So this is a typical proving a theorem. So here are some axioms. And here's a theorem that P NAND Q equals Q NAND P. You take a series of steps here. Well, this is a particular path through here. In general, this is a multi-way system. And in general, well, there will be many paths, but in general, there'll be a multi-way system that you form that corresponds to all the possible ways you can apply axioms to generate a particular result. And so a proof is a path through this multi-way graph. Okay, so now one of the questions is, what is the bulk limit of mathematics? And how do we think about that? What is the limit when we've got 3 or 4 million theorems in the published literature of mathematics? What's the infinite time limit of mathematics? So we go on developing mathematics forever. We have trillions of theorems. What can we say about the overall structure of metamathematical space and so on? All right, before we talk about that, I need to talk about one other idea. And that idea is a thing we call the ruliad. And here's how this works. So let's say we have a model of physics, and we've discovered that we can model the universe with some particular rule of physics, with some particular underlying computational rule. Well, that's a pretty weird situation because we're saying there's this little rule, I can hold it in my hand, and it's going to give me the whole universe. And then the next question will be, why did we get this rule and not another rule? You know, from Copernicus on, we have believed that there's nothing special about us. So why would we get this particular rule, this particular simple to us rule? Why would that be the one we got for our universe? So the thing that I realized is that, in fact, it's a more complicated story. So in this multi-way graph, we're talking about the idea that at every step, there are many possible places we could apply a particular rule. But what if we go even further than that? If we say, well, not just applying any particular rule everywhere, but applying any rule we feel like, any possible rule. So the that leads us to this idea of what we can call rulial multi-way systems. So let me show you an example of that. Let's see. Oh gosh. Sorry. I don't know exactly what I'm going to talk about here, so it's hard to be. Okay, so let's talk about rulial multi-way systems. So here's a Turing machine. There's its particular rule. That's a particular deterministic Turing machine. There's a non-deterministic Turing machine. It has multiple possible paths of history. But what if we take the rulial limit of Turing machines? We say we're going to look at all possible Turing machine rules, and we're going to ask what happens with all possible Turing machine rules. Well, then we'll generate a rulial multi-way graph where we might start from this initial condition, and these edges correspond to all possible Turing machine rules. Now, you might say, if you just can follow any possible Turing machine rule, you're going to get a trivial structure, but you won't. And the reason you won't is because two different Turing machines might lead to an equivalent state. And so there's all these entanglements and equivalences that you get. And so the final thing you get is actually not a trivial structure at all. This is just a simple rulial multi-way system for Turing machines. You can go and you can understand things like if you look at the deterministic Turing machines, there's the deterministic Turing machines. There's all possible Turing machines. The story of P versus NP is the story of whether the red bit gets out to the gray bit, basically. I mean, it's a sort of geometrization of P equals NP. But this is the structure of rulial space for Turing machines, the structure of what you get when you follow all possible rules. Okay, so now let's say this is how the universe works. Let's say we can follow any possible rule we choose. We are just going to enumerate rules. We're going to enumerate initial conditions. We're going to run them for an infinite time. What is the thing we get? It is the entangled limit of all possible computations. And it is a definite thing. And it's a thing I've called the ruliad. It's this entangled limit of all possible computations. And the thing that's remarkable about it is it has a huge amount of structure. You might have thought it doesn't have any structure at all. It has a huge amount of structure. Mathematically, it is rather related to things like infinity groupoids and so on, and the way that those things work. But in any case, for our purposes, the ruliad is this thing that is the entangled limit of all possible computations. Okay, now let's think of that as being our universe, the ruliad, but now we are observers embedded within the ruliad. And as observers embedded within the ruliad, we are picking a particular sampling, a particular slice of the ruliad to represent our perception of reality. And so the question then is, well, what can we say, given that we have this ruliad, it's all possible entangled computations, but now there's a crucial other piece of information. We are an observer like us. We're an observer that's computationally bounded, that believes we're persistent, et cetera, et cetera, et cetera. What does that mean we perceive from the ruliad? Well, it turns out to mean we perceive the laws of physics as the laws of physics are. So in the sense, it doesn't matter what the underlying rules of the universe, the universe is running all possible rules, but our sampling of this corresponds to a particular rule. So for instance, the story okay, so one question is, how localized are we in rulial space? Do we believe the universe follows only one particular rule? If that would mean that we are localized at one point in rulial space. Well, this is a story of scientific induction, because basically to know where we are in rulial space, we have to have been able to do perfect scientific induction. If we want to localize ourselves completely at one place in rulial space, that means we've perfectly nailed how the universe works. But in practice, we do scientific induction. We make experiments, we do a finite number of experiments. That causes us to not be localized in rulial space. We're slightly unlocalized in rulial space. We have some uncertainty in what the laws of the universe are because we only have sort of finite scientific induction. So that's so this idea is there's this ruliad, which is an inevitable, a formally necessary object. There's nothing about it that could be changed. It is the limit of all possible computations. Well, there is one thing about it that could be changed. We can make a hyperruliad, which involves oracle Turing machines and things like that. But there is always an event horizon between the ruliad and the hyperruliad. So there is a ruliad. It is this definite thing. It's made from all these computations. It is, in a sense, a formally necessary, inevitable object. There's no choice. There are no choices about it. But there's a big choice for us as observers of the ruliad. We are at a particular place in rulial space. that we take a particular sample of the ruliad. And that's what leads us to our particular perceptions about the world. And it's one feature is that for observers like us with these attributes I've mentioned, it is inevitable that we will perceive the world to have these attributes like general relativity and quantum mechanics. Beyond that, it is a question of where we are in the ruliad, how we will perceive other features of the world. And so, in a sense, you can think of this sort of position in the ruliad as the contingent fact about how things work. We look at the world from a particular viewpoint. We're a particular place in physical space. We're a particular place in rulial space. That's how we perceive the world. So if we imagine the aliens somewhere, the aliens may be separated from us in physical space, but they may also be separated in rulial space. What would it mean if they're separated in rulial space? It means that their perception of how the universe works may be completely different. It may be that they, where we think about space, they don't see space at all. They just see all these details, et cetera, et cetera, et cetera. And so this idea that sort of the contingent thing is where we are in the ruliad. And the one sort of key contingent fact is that we live in the ruliad and not in the hyperruliad. And that leads us to the principle of computational equivalence and the way that it's set up, et cetera, is a consequence of that fact. So, okay, so we've got this ruliad. It is a formally necessary object. We live inside the ruliad. We sample the ruliad. With the samplings that we take, we inevitably end up concluding that we see certain features of physics. Okay, so one other piece about this, several other things. So one question that comes up a bunch and is, why does the universe exist? Why is there anything? Well, one thing to realize is the ruliad, as we've set it up, is a formally necessary object. It's not something where we can reasonably ask, why does it exist? It's something which exists because of the nature of how you define things. It's a necessary object. So then the question and then the issue then is why. This is a longer argument. Let me not go into this. I've written a whole piece about this. But the end result is that from the sort of the necessariness of the ruliad combined with this sort of contingency of where we are within the ruliad is the reason that we perceive the universe to exist, so to speak. This is the argument. Now, okay. Here's where things get funkier. So this ruliad consists of all these entangled computations, et cetera, et cetera, et cetera. Well, we think about that as making physics. But what about mathematics? Mathematics is the same kind of thing. I showed you, a mathematical in axiomatic mathematics. You have this idea that you can, make this multi-way graph, and the theorems of mathematics correspond to paths in the multi-way graph. Actually, there's a different formulation. It's a little bit better that are called accumulative systems, where the actual nodes in the graph are propositions or mathematical statements, and you basically start off with a mathematical big bang of your of the axioms you start with, and then you derive all these other possible axioms. You derive, just like in physics, there's a light cone where you start from an initial event. In mathematics, you would have an entailment cone where you start from an initial sort of big bang of things that you assert, and then you get this entailment cone of things that follow from that. Okay, so but now we're thinking about mathematics is also something that is in the ruliad. So because all these different mathematical theories, all these axiomatic theories and so on, they all can exist within the ruliad. So then what we're seeing is mathematics and physics come from the same place. They're both samplings of the ruliad. Physics is a sampling of the ruliad that's based on our particular sensory systems and the fact that we perceive space and time and so on. Mathematics is a different kind of sampling of the ruliad. And so one feature of that, one philosophical feature of that is that if you believe that the universe exists, then you also have to believe in some Platonic sense that mathematics exists. And you have to, in other words, this argument is showing one that in some sense, mathematics is as existent as physics is. But let's go into this in a bit more detail. I've been writing this thing, which is now about 200 pages long, about the physicalization of metamathematics. And it's about the question of when you think about metamathematics, when you think about the structure of metamathematical space as, let's see if I can show you an example here. Well, sorry, this is very hot off the press, so I literally have to show you pieces of, okay, there we go. So there's a typical accumulative derivation. Oh no, no, that isn't an accumulative one. That's just a simple multi-way derivation. You can make a branchial space. That branchial space is essentially a map of mathematical theorems, ends up being a map of mathematical theorems, and you can start asking all kinds of questions about this. And there's, for example, let's see. You can, okay, so these are some entailment cones. So these are entailment cones for actual, those are very simple mathematical theories. Those are the entailment cones. Now, so every true theorem of this mathematical theory must exist in this entailment cone. It may take a while to get there. And by the way, false, the notion, this is a very constructive idea of mathematics. You're just starting from this theorem and you're building up every possible true theorem. What does false look like? False is a kind of rulial virus where you have this sort of explosion of, it relates to this principle of explosion for falsity that you get that, but that's how false comes out. So for example, you can ask the question, given a particular collection of axioms, this is, so there's a bunch of axiom systems, there's a bunch of theorems. This is showing which theorems are true for which axiom systems. And now you can ask the question, well, if we just look at that from the entailment cone, we say, how far do we have to go in the entailment cone? This is 2 steps in the entailment cone. That's all it gets to after 2 steps. Those are the theorems that we've established from the entailment cone. In the end, the entailment cone will establish every one of these theorems. But these are the theorems we here are sort of directed paths, directed efforts we can found using automated theorem proving, directed sort of explorations of the entailment cone. Just the natural entailment cone is generating oodles of other theorems, which don't happen to be the ones that are short and that we might care about here. So in any case, we're looking here at, we're thinking about sort of the structure of metamathematical space. And one thing to realize is that the axioms, thinking about things in terms of axioms, I don't think is actually the right level. So here's an analogy. So most actual mathematicians think about mathematics not at an axiomatic level. They think about mathematics at a level of structures and mappings and category theory and things like this. And if you say, well, what's mathematics actually based on? They probably will say, well, it's based on set theory at some point. But that's not how they actually work on things. And I think the analogy you can see back all the way to statistical mechanics. Axiomatic mathematics is like molecular dynamics. Actual mathematics, as done by pure mathematicians, is like fluid mechanics. And it turns out it doesn't even matter in detail what the underlying axioms are in many cases. You can say, I've got the Pythagorean theorem. I'm going to deduce things based on the Pythagorean theorem. What is the Pythagorean theorem? Oh, I'm going to make this assumption about real numbers. I'm going to make that assumption about real numbers. It's differently set up axiomatically, but that's okay. It doesn't matter. At the level of the fluid mechanics, you can still deal with it as just the Pythagorean theorem. It's really a cloud of things in axiomatic space, so to speak, but it's still considered the Pythagorean theorem. So here's a key fact about this. So the question is, if we think about sort of the Pythagorean theorem and using it and essentially moving the Pythagorean theorem around in some kind of metamathematical space, the question is, does the Pythagorean theorem get shredded? In other words, so if we are objects in physical space, one feature is that we can move around in physical space and we don't get shredded into atoms of space. We can think of ourselves as a lump of atoms of space that is somehow persistent and maintains coherence as we move around. By the way, even in general relativity, if we're near a space-time singularity, we will be shredded by just moving around in physical space. But the fact that most of the time that doesn't happen, that means that it's consistent to view us as being persistent and to have the idea of pure motion. So the question is, what's the analog of pure motion in metamathematics? The analog of pure motion, I think, is that you don't get shredded. The Pythagorean theorem doesn't get shredded. It doesn't matter that there's different axiomatic foundations for the Pythagorean theorem. You can still just use it as the Pythagorean theorem. So in a sense, the fact that you can do higher level mathematics is a consequence of the idea that for something like a mathematical observer like us, you are able to kind of move around in metamathematical space and not get shredded. Now, I mean, this is a much longer story, and maybe I shouldn't go into it in more detail here. But another thing to realize is the axioms are not the lowest level of mathematics. The axioms, you can make the axioms out of something lower level. For example, just for fun, we started making some out of combinators. But you can make them out of any of the raw material of the ruliad. And in a sense, what happens is the number one can emerge in many different ways from the raw material of the ruliad. The thing that you identify as the number one is this cluster of sort of atoms of existence, calling them eames, these sort of atoms of existence. There's some clump that we identify as the number one, and that will be combined with some other clump that we identify as the number two, and so on. There are many different ways we can make that identification for the number one, the number two, and so on. Those correspond to different reference frames, different samplings of the ruliad, different, in a sense, mathematical reference frames. But what's happening is we're emerging from the level, from the raw ruliad. What emerges are these objects, which we can then parameterize using axiomatic mathematics in terms of sort of axiomatic systems if we want to, or we can go straight up to the fluid mechanics level and see what that implies for the sort of structure of mathematics. For example, does it imply category theory? Category theory, I think, is that there's an important set of principles which have to do with the homogeneity of metamathematical space. And I think the existence of dualities between different fields of mathematics, the fact that you can transform between different fields of mathematics is essentially a statement of the homogeneity of metamathematical space. That's the analog for mathematics of the possibility of pure motion in physics. So, and by the way, then you can ask questions, well, in this kind of picture of metamathematical space, you can ask questions, what's the future of mathematics? Well, for example, what's a black hole in mathematics? A black hole in mathematics is basically a decidable theory. So in physics, a black hole is something where, in our models at least, where time ends because you essentially have these rewrite rules and you reach a normal form where there are no rules still apply. So time ends. For the observer and for the universe, time has ended. And it's the analogous thing in metamathematics, I think, is the appearance of decidable theories. And in fact, you can even make a very definite analogy, details not fully in, that when you have too high a proof density, you inevitably form a singularity in the same way that the singularity theorems work in space-time. You inevitably form a singularity which corresponds to a decidable theory. So the picture of the future of mathematics of kind of, there's a lot of these burnt out decidable theories together with this sort of expanding metamathematical space. By the way the mathematical observer works is a little different from physics observers. Physics observers are very time-based. Mathematical observers, in the way ordinary mathematics is done, form these kind of entailment fabrics that are pieces of space-like hypersurfaces, not the usual time-like thing. When you do kind of mathematical experimental mathematics, you're doing the kind of time-like discovery of mathematics that's analogous to what happens in sort of our time-like discovery of the future of the universe. But when you do more traditional mathematics, you're forming these entailment fabrics that just work a little differently. But the key point here is that in the end, the possibility of high-level mathematics, I claim, is related to the fact that mathematical observers like us go from the raw ruliad to something where there is a continuum limit, and that continuum limit is what leads to the possibility of having higher level mathematics. If it wasn't for the existence of that continuum limit, if it wasn't for the fact that there is something like sort of continuous metamathematical space, it would be the case that we would always be thrust down. Every time we try to do mathematics, we'd always be grunging down at the level of the machine code. We'd never be able to get these higher level concepts and operate at the level of these higher level concepts. And by the way, when we, in studying the computational universe and studying simple programs and things like that, you are sort of casting out into this sort of arbitrary place in the ruliad. And so it's a little different from what, the question which I've long been curious about is, why is undecidability not more common in everyday mathematics? The answer is undecidability, I think, is not more common for the same reason that molecular dynamics is not important to fluid mechanics. That is, there is, for an observer like us, there is a fluid mechanics level of mathematics, and it's not, and you're not seeing these sort of underlying axiomatic structures which lead you to undecidability and so on. That's not a common thing. You have to do a very specific experiment in the traditional view of sort of mathematics as fluid mechanics to see undecidability. When you cast out into the computational universe, when you launch a rulial spacecraft, so to speak, where you're anyway, sorry, I'm now starting to look at chat, and I shouldn't do that. So the question is, we can sort of think of ourselves as launching a kind of when we go beyond traditional mathematics and we do experimental mathematics and so on, we can think of that as sort of launching a rulial spacecraft that's going to a different place in rulial space. So, going back for a moment to consciousness, and then I'll wrap up here. I mean, I think that one of the things that I think this concept of rulial space is kind of interesting for consciousness. It's kind of a way to think about, what's the difference between you and me, so to speak. It's like we're in different places in physical space. We also are effectively operating in different places in rulial space. All of us are pretty close in both physical space and rulial space, but we're not. That is sort of the difference, in a sense. It's potentially a way to view the difference between different consciousnesses is the fact that they are in different places in rulial space. Nevertheless, because of things like causal invariance, because of the general properties of the ruliad, which are related, I think, to all these things in higher category theory and all these other places, that because of all these properties, there is a certain objective reality that exists. Even though we're at different places in rulial space, taking different samples of the ruliad, we still perceive the same features. And the main point to make about sort of general physics and mathematics is, although the details are different depending on our particular position in rulial space and so on, the key fact is observers like us, computationally bounded, believe in persistence and so on, inevitably it follows that the laws of physics work the way they do. And I think inevitably it follows, and I didn't go through all of the argument here, but inevitably it follows that high-level mathematics is possible. And that, which I think is not a self-evidently true thing. It is something which turns out to be true for observers like us, for doing mathematics, thinking about mathematics the way we do, which I think ultimately is deeply rooted in the way that we perceive physics. And this relates to the question of, can you directly see the truths of mathematics, or are you sort of forced to go through the axiom systems and so on? And we can talk a bit about that.